So this is my data set. Okay, I am the reading this CSV file, and this is the diabetes data set. Using this data set, we have to build a model, and using this model we have to predict that if this patient has a diabetes, then give me output 1. If this patient does not have a does not have a mm, diabetes, give me output 0. Now you have to predict that is this patient has a is this patient a is that patient a diabetic patient or not. We have to build that model. So using logistic regression we can build that model. So if I do the bandage profile reporting to know more about this data, so we can know that there is a 8 numerical, 1 categorical, 8 numerical column, and 1, this is the categorical outcome is categorical. And if I this is not a normal distribution. Okay, if I go to this data details, this is, if you, this is a bar plot, it is not a normally distributed, it is a right skew, left skewed. Okay, and this is the approximately, this is the normal distributed, you can take it. Okay, this is also normal distributed, but there is outliers, we have to remove that outliers. And if you there is a 35 0. One thing you have to more, you have to read about this data set details, because if you see that 35 people have a 0 blood pressure, it is not possible. Maybe the machine does not take the blood pressure properly, because 0 blood pressure means the people is dead. So also the glucose 0, 0.75% glucose 0. It is not possible that one person have a 0 glucose. Okay, because it then means people is not alive. So some, the many, we don't have to change all the 0 value, but sometimes this type of glucose blood pressure, it cannot be 0, because it is a essential essential thing for a alive person, so it cannot be 0. Thick thickness, skin thickness, so 0 to 27. Okay, insulin 0. It cannot be, insulin cannot be 0. It is a, if you know the life, biology, you can understand that it cannot be 0. So you have to remove this type of 0. BMI, okay, 0 11. Diabetes prediction function, okay, age 0 0. Okay, there's all in outcome. Okay, and one thing I want to one thing I want to tell about that, that pregnancy. If you know the pregnancy, the 0 1 1 1, the 0, we don't have to remove this 0, because maybe the some people, not every people will be pregnant. Okay, so there maybe there is some unpregnant man or woman. Man cannot be pregnant, but you can, there's some women can be not, there's some women that are not pregnant, so it can be 0. So it is a, it is justify data, so we don't have to change this 0, but other 0 we have to, you have to change that, we have to modify that, we have to fill with mean value. And this is the graph about correlation. So if we have a high correlation, then we have to drop this data, we just drop that column, because we have to check this multicollinearity. If you know that concept multicollinearity, then you can understand that. If I know that glucose and BMI, it is not a high correlation. If you find that correlation close to +1 or close to -1, if between two column, then we have to drop that column, because it is not good for, for build a model. So in this case there is a no multicollinearity, there is a no high correlation, so no problem, we don't have to drop the uh, column, because there is a no multicollinearity. Multicollinearity means if there is a two feature and there is a high relation between two feature. It means if you have a relation between outcome and BMI, that's okay, but if you feature relation between insulin and thickness, that's not a good thing, and there's a missing value, we have to deal with the missing value. This is the pandas for ending the pandas profiling. Then if we know that the columns, all are the columns, and we have to deal with the zero, missing zero value, missing value. So the all zero value we have to fill with the replace with the mean. So here we are replacing all zero value with the mean value. Also the glucose, blood pressure, same thing. I am replacing zero with their mean. Insulin thickness. And plot the data, if I plot the box plot, because we have to remove the outliers, because we have to normalize the data before building the model. We have to normalize the data. In our model we have a skewness, right skewness, left right outer skewness, right or left skewness. So we have to remove the outliers. um, so we have to draw the box plot. So using the block plot, we can if you see there is some outliers. There is outliers, the density is more. Okay. And also this is the high outlier. There's lots of outliers here. It is a outlier, it is also outlier, there is some outliers here. So you have to remove this outliers using the quartile function. Quantile function, if you know that concept, the outer quartile. So it means that if you add insulin have a lots of outliers. So we have to remove some outliers. So here uh, here I am doing that quantile 0.70. It means it will take 70% data, and 30% data will be deducted, removed. Using that this concept we are deducting. It means I want to take that. I want to take this type of data. 70% data I want taking, and I am removing 30%, and the high, 30%, high, what I can say, 30% जो मतलब क्या बोलते हैं उसको, 30% आउटलायर में रिमूव करना चाहता हूँ. I am taking that 70% data. 0.70 means I am taking only 70% data and removing the 30% data. If I do the like that, and if I build that data frame, it will be like that. When I removing some data, we will lose some data. It is okay to lose some data to reduce the outliers. If you know the original data, there is a 768 and 9 columns, and there is when I reducing the data, we are taking 70% in insulin data, then only 536 row, because we have losing the 30% data, because when I dropping the insulin data, the whole row is dropping, gone. So that's why the data is reducing here. So here also we are doing again doing that box plot and using new data. So after doing that, do the outliers for insulin like that. Previously insulin like that, but now insulin like that. We also remove because all outliers, impossible to remove the all outliers. We have to reduce also these outliers. So okay, so we are in this case, after this analysis, we are removing 2%. We are 2% pregnancy outliers. We are taking 99% BMI and removing 1% outliers data. We are taking 99% six thickness data and reducing dropping that 1% data. Here we in insulin, we are taking 95% data. We are building a new data frame. That's why we are doing that. 90% data, because there are lots of outliers. So you have removed that 95% data and taking 95%. We are dropping 5% data and taking the 90% data. And in the database diabetes prediction function, we are taking 99% data, removing 1%. So using that, we are building a new data frame, df new. If I plot this data box plot, then you can see that there's a lots of there. If you there's density, density, the reducing, we are reducing the density. Also we are reducing the some outliers here. you are reducing some here, we are reducing completely here, uh, we are reducing here, we are reducing here, we are also reducing here, because there's just some there's a more density here, but we are reducing the density in this case. Okay, so insulin now, one thing you should remember that we unable we cannot be remove the uh, we cannot remove the all outliers using this quartile function. Okay, we cannot normalize the data using that quartile. We can use scalar function, standard scalar function to normalize the data. Using this quantile function, we are reducing some outliers. After this quantile function, we can use scalar method to normalize the data. It is okay to do the both in the both way. Again, we are this is the original data. This is original. If there is lots of outliers, but in the new data, we are reducing some outliers. Okay, that's okay. And we are also doing the Pandach profiling report for the new data. And if I know the df dot columns and df new data frame, and after then we are separating the data into x and y. Okay, after reducing the outliers, it means we are now normalizing, we are trying to normalize data, but maybe if I go to that dash profiling, let's see one thing, what happened. Toggle details, the standard deviation is 2.22. It is not a normalized. If you know that, if you this is the normalized data, it is the standard deviation will be 1 or related to 1, you know. So but this is the standard deviation, very high standard deviation. It is not a normalized data, but we are trying to normalize, but it is not, we are not able to do it. That's okay, because we can normalize the data after this method. We can normalize the data at a training time using scalar method. So forget about normalize, we will do it later. So then we are now try to separate the data and separate data into x and y, because we have to do training and testing. So uh, we have to separate the data. So this is the outcome. So we are taking y as outcome and output, and in the x we are dropping outcome. We are dropping outcome, because we have to train this we have to train the model using this input value. So we are dropping that output. So using, after dropping, x will be like that, and y will be like only output. So after, if I able to show you how how will be y you will be like that, 1100, and x will be like that. We are removing the dropping the outcome column from new data frame. And after then we are using standard scalar method, transformation method, to reduce the fluctuation of data. If you see this data, there is a lot of fluctuation. If the 85 of 1480, 122, so 93, and if you're going 6 1 10 2, also like that 70, 180, 79, 122. So it is not a stable data. We have to stable the data. We have to reduce that fluctuation, the data fluctuation, to normalize the data. Because because this type of variable like 180, for this type of data we are get outliers. In the previous method we are try to reduce some outliers, we are able to reduce some outliers, but not, not, we are unable to remove the whole outliers. But using it's a standard scalar, we are reduce that value. We are reduce the scale, we are transfer into different scale. So using using that standard scalar method, we can do that normalize data normalization. We can do that data normalization. So after using scalar method, we are doing that Pandach profiling. And if you see now, if you know, we pregnancy is not a normalized now, but this is the normalization. Like if you know that this is a normalized, that is also normalized, this is also normalized. It is one outliers, very normalized. But if you see that standard deviation of one, now it is a one. If you see the standard deviation of one, so it is a normal data. It is a normal. It is also normalized. It is also normalized. It is you can it is not a normalized, but it's a right skew. That's okay. You can take it either one outlier here, and approximately normalized. If I see the standard deviation, if I okay, standard deviation is what is the standard deviation now? 1.0. It is near to normalization, but not properly normalized. So yeah, after then there is no high correlation, so we don't have to remove any data. We don't have to do. Don't have to drop any column. That's okay. So we don't have any multicollinearity. We also data is normalized, and we also we also resolve the missing value. That's okay. And also here also doing transforming, we are using scalar method and plotting that. After transforming using standard after using scalar method, we are plotting, we are doing box plot and see the difference. There's a lot of fluctuation in the previous data, but in this case the box plot is more stable. If you saw the, if you can see the the changes is reflected here, because they see that the data in the same range, no, previously there's a lot of fluctuation, but in this case data is more stable than previous data. You will not able to do 100% because it is impossible, but approx it is just stable than previous data, the given data. And also we are reducing that outliers. Yeah, we are reducing the density density of the outliers. So that's okay. Now all we are also doing that x, we are split the data using split it we are split the data in two parts, x and y. So we have to transform the data. So we are transforming x data. So standard scalar deviation and scalar dot fit transform x. We are we are normalize the x data, and also you have to normalize y data. No, we don't have to normalize the y data because we have to, because there's a 1 or 0, so you have to don't normalize it, because it is output. So the x after normalization, x data is like that. X cult, we are rename that x data is like that. After we are divided df new into two data, x and y. Okay, x data for train the model, and y for y is the output here, expected outcome. Now check multi-collinearity. There is another method of checking collinearity. Uh, so yeah, the VI score, the VIF score. So using this, this function, you can check VIF score. But if you give the x data, this data is not normalized, because x is given data by the data set. uh, so if I give that given data, not a normalized data, VIF score like the 1.1. If the VIF score is not greater than 10, so we don't have to drop that column, because if it is a 10, then it means there is a high correlation between two features, and there is a multi-collinearity, so you have to drop that data. But in that case there is a no multi-collinearity, I told you previously, and it is a proven now, because we are checking the multi-collinearity here using VIF score. Okay, and after then we have to split train and split the data. We have to training the data. So after for the training the data, we have to split the data. So here we are split x scale data into four parts: x10, x test, y test, and y test. So after the and we are giving that y output level, and test is to 0.20. It means we are taking 20% of data for testing. A random state means it will fix the data for each time you for every time it will give the same same value. It will fix that value. If you know that proper meaning, you can understand that. So this is the extent, this is the y test, this is the y train, and this is a y test. Now building the model, so we are calling that a logistic regression function here. And regression function verbose one means verbose one used for logging. Okay, and we are fitting that model using external y train. After then we are getting that extern is that x test is that, and y test is that, and that. So we are building that, we are now train that model, we are all build that model. So we have to predict that model, we have to predict the accuracy of the model. So logr is my model. So logr dot predicts x test 0. So it gives the 0 class in prediction. If you see the prediction 0, array is 0, it means using this, if you if you able to x0 is means this data one, this is the x0 data. X test 0 data, this is the x test data. If you predict using this data, it will give 0 class is a output. It means this patient does not have a that doesn't have a diabetes. Using predict probability model, it will give the predict probability function. It will give the probability for being a diabetes, being don't have a diabetes. It is a 0 class, it is a 1 class. It will give probability for both class. It is also give you the sign. It it means the log probability means it will give the sign. It will be above the line or below the line. So for the 2, for the 0, for the 1, it will give the probability. And if I match this, we are predict that it will be 0, but in expected we are expecting 1. What is I log 1? So it is not matching. In this case, the prediction of model is wrong. But if I take another example, like x test 1, using the x test 1, we are getting 0 as output. He is predicting the this data. This person does not have a diabetes. If we are using this function, we are getting probability for the for 0 class 0 class 1. Using log probability function, we are getting now a probability minus 0.847 2 minus 2.48. Are using y test silo. If I so we are getting the predicted value 0. Also using this type of using after seeing this value, we can guess that the prediction will be 0, and also it will give that the output, the predicted value is 0 by model, and expect is also 0. So it is a matching. So our model is working uh, for working fine for 90% case. 10% will be we are doing prediction, so it may be some cases we are failed. It's okay, that's okay, because we cannot be able to do 100% accurate model. Um, so in this case the accuracy is matched. We are able to predict that person's diabetes successfully. If I build another model, so there is a concept called solver. There is a various solver. You can go to that official documentation of the scikit-learn logistic regression. You can know that. So if I using another solver, linear, so it will if it will implement some what I can say, it will implement some election, some um, some method to reduce, like L1 L2 regression, elastic net, something like that. They will reduce your so if I one thing, 1 minute, shift tab. Solver, if you go in this thing, the by default the solver is LB FGS, and but in this case we are using linear. So in the in the multi, if you can read the documentation, regularized. So using this this type of option, you can regularize that model. Linear use linear library L2 regulation. So if you know about the regulation, you can understand. So using different solver, we can we can build different model. First, by default, the it will use the LBGFS solver. After then, we are using linear. So we are building two model. We are building two model. So we have to predict using two, we have to predict using two model. We have to see which model is accurate. So here we are giving this data, and the output is predicted. Or here also we are using default by default model. So it will give this model, this output. And if we know the confusion matrix for find accuracy for linear model, using the linear we are build a ML model. So this is the confusion matrix, and using the by default we are by default model like that. This is the by default we are this is the by default model. Mm. So using this model, if we if we find the confusion matrix, this is a 7 10 24. In both cases the confusion matrix is same. So what that means that the accuracy of the of two model is same. And if I using this model, we are find accuracy, precision, recall, specificity f1. If you know that if you know the statistics, you can understand that. Also using this model we can find the default valued accuracy prediction f1 score. Using this function, we are finding the that linear model f1 accuracy and specificity. And we are finding also AOC, area under curve, 0.957 per linear, and default is also 0. Also area under curve also 0.69. So in the both cases the AUC area under curve is same. It means the both model is a same accuracy. It will give the same accuracy. If you build a multiple model, then you can choose your model using AUC, area under curve. And we are also drawing this function. We are drawing the area under curve graph. So this is the whole no Python notebook. I am doing this is a whole Python notebook, and this is my logistic regression practice. So I hope you are understand. You are able to understand what I am trying to do it. So we are building a logistic regression. We are building a model by using logistic regression, and we are finding the accuracy of that model. Will give that best prediction for me. Which model will give prediction on me? In my case, both model will give that same accuracy. Thank you.